Okay, today our first goal is to extend the functor k0 to non-unital rings. K0 for non-unital rings. Well, we can try to define k0 for non-unital rings in much the same way as we did in the unital case. That is, to define it as the Grothendieck group of a certain semigroup constructed from finitely generated projective modules, or equivalently from idempotents in matrix rings. However, this is not a good approach. The resulting functor lacks some important properties, and so it is practically useless. Before we give a proper definition of k0 for non-unital rings, let's introduce some terminology. We will work with the category of all rings, not necessarily unital. So let's denote this category like this. So this is the category of all that is not necessarily unital rings. And we give the following definition. A ring extension is a diagram in this category with the following form. A diagram of rings such that if we forget about multiplication and consider this diagram in the category of abelian groups, then the following sequence, if we add zeros on both sides, is exact in the category of abelian groups. Sometimes we say that we have an exact sequence of rings, but we must remember that there is a slight abuse of terminology here because the category of rings is not additive. And in general, it makes no sense to speak of exact sequences in non-additive categories. So what we mean is that the resulting sequence of abelian groups is exact. Let's observe that in this case, if we have a ring extension, then the image of the ring I under this map little I, so of course it can be identified with I because little I is injective. So it is the kernel of P, and so it is a two-sided ideal in R. It is a two-sided ideal, and we have the following commutative diagram. So this is I. It can be identified with little I of I, its image under this map little I. Here we have the embedding into R. And here we can take the quotient of R modulo I, modulo the kernel of P, that is modulo I. And here we have a quotient map. And clearly, these two rings, S and R over I, are isomorphic in such a way that the diagram commutes. So S can be identified with the quotient of R modulo I. So in summary, we see that a ring extension is completely determined by this ideal I. And of course, in most interesting cases, I is not unital because it is a two-sided ideal, and the two-sided ideal is not necessarily unital even if R is unital. Okay, now I can explain what we want to achieve. So our goal is to define K0 on the category of all rings in such a way that for every ring extension of the following form, the respective induced sequence of K0 groups, K0 of I, K0 of R, and K0 of S, is exact. This is what we want to achieve. And the respective property of K0 is called half exactness. Of course, a natural question is what will happen if we add 0 here and consider the respective short sequence of a billion groups with zeros on both sides. Is it exact? Well, in general, the answer is no, and this is the reason why we have only half exactness, why we call it half exactness. The exactness is too much to expect. So K0 is only half exact. In general, this map is not necessarily injective, and this one is not necessarily surjective. Okay, so this is our goal. And to achieve this goal, let's now look at a very basic ring extension, which comes from the ring unitization. If R is a ring, then we can define the unitization of R in much the same way as we did in the case of complex algebras. That is, we consider the following abelian group. So the only difference with the case of algebras is that we replace the base field of complex numbers by the integers. And we equip this group with the following multiplication, which is defined exactly as in the case of algebras. If we have two elements of this direct sum, then by definition the product of these two elements is Rs plus Ks plus Lr plus KL1. And exactly as in the case of algebras, we see that this is a unital ring. And this ring has the same universal property as in the case of algebras. So here's a simple exercise. First of all, for every ring R and for every unital ring S, we have a bijection between a set of all ring homomorphisms from R to S and a set of all unital ring homomorphisms from the unitization R plus to S. And this bijection looks exactly as in the case of algebras. And moreover, again, exactly as in the case of algebras, the correspondence which takes R to R plus is actually a functor from the category of rings to the category of unital rings. So it is natural in R. And it follows from the previous picture. In fact, this picture is natural, and so this functor is left adjoint to the inclusion of unital rings into all rings. Left adjoint to the inclusion of unital rings into the category of all rings. Okay, so this is the unitization of a ring. And let's now observe that we can construct the following ring extension let's define epsilon, map epsilon from R plus to the integers, which takes every element of the following form in the unitization to k. So it projects onto Z. So this is, of course, is an algebra homomorphism. And we have an extension of the following form. R is embedded into R plus as a two-sided ideal, and R plus is projected onto the integers. And clearly this is a ring extension. Well, now epsilon of course is a unital. I said algebra, of course. At this point we work with rings. So it is a ring homomorphism, moreover it is a unital ring homomorphism. So K0 is already defined for R plus, for R plus, and for Z. So now having in mind this goal, it's natural to define K0 of R to be the kernel of the induced map epsilon star, which acts from K0 of R plus to K0 of Z. So this is quite natural if we want to achieve the half exactness. Of course, there is a delicate point here. Strictly speaking, I must denote this group in a slightly different way. So let me put, for example, a prime here. For the simple reason that if R is already unital, then K0 of R is already defined. And it's not immediate that this new definition agrees with the old one in the case where R is unital. In fact, it agrees, but this is not entirely immediate. We'll see this in a few minutes. So anyway, well, let's now make another useful observation. Let's observe that epsilon is not just a ring homomorphism, it's actually a retraction in the category of rings. It is a retraction in the category of unital rings, actually. In other words, there is a section, that's denoted by eta, which acts in the opposite direction and takes every integer to the following element of the unitization. So, and clearly it's a unital homomorphism, and epsilon eta is the identity map. So epsilon is a retraction, and since K0 is a functor, we deduce that epsilon star, which acts from K0 of R plus to K0 of Z, is also a retraction in the category of abelian groups. And as a result, we see that we have the following split exact sequence of K0 groups. K0 prime of R, K0 of R plus, and K0 of Z. And this is epsilon star. A split exact sequence of abelian groups. Well, just in case, let's briefly recall what split exact means. So a short algebraic digression. So we have the following definition, which is at the same time a theorem and an exercise for you. So suppose we have a sequence of, for example, of R modules over any rings, over any ring R. Sequence of the following form, say M and P. And we say that this sequence is split exact. Split exact. if it satisfies any and hence all of the following equivalent conditions. Condition 1, so let's denote these arrows, for example, alpha and beta. So condition 1, the sequence is exact. It is exact. And beta is a retraction. That is, it has a right inverse morphism. Equivalent condition 2, it is exact. And the alpha is a co-retraction, which means that it has a left inverse morphism from n to m. And condition 3, this sequence is isomorphic to the following direct sum sequence. So here we have m plus p. So there is an isomorphism between n and m plus p, such that if we here embed m onto the first summand, and here we can project m plus p onto the second summand. So mp goes to p. Then we have the following commutative diagram. So in this case, we say that our sequence is split exact. Of course, if we deal with vector spaces, so if R is a field, and we consider vector space as sort of a field, then every exact sequence is split exact. It's quite easy exercise in linear algebra. But already in the setting of abelian groups, this is not true. So there are many natural examples of exact sequences which are not split exact. And this follows from the fact that not every module is projective in general. So now coming back to the sequence, we observe that it is indeed split exact because, well, epsilon star is a retraction, and in particular it is surjective. And the sequence is exact here and here just by definition of K0 prime of R. K0 prime of R is the kernel of this map. So the sequence is exact, epsilon star is a retraction, so the sequence is split exact. Okay, let's now observe that this functor K0 prime is actually a functor. It is natural in R. Functoriality of K0 prime. Well, indeed, suppose we have a ring homomorphism, say phi, from R to S, a ring homomorphism. We extend it to the unitizations. So the unitization is a functor. So we have a ring, a unital homomorphism phi plus from R plus to S plus. And we consider the following diagram. So we have here K0 of R plus epsilon K0 of Z. And here we have a similar picture for S plus. So this picture comes from the respective diagram of rings. So let's draw it here. So R is embedded into R plus and is projected onto Z. And S is embedded into R plus and is projected onto Z. So we have two ring extensions. Phi plus extends phi, obviously. And here we have the identity map on the integers. And clearly the diagram commutes. Oh, sorry, here we have S plus. S plus. So the right half of this diagram, is the diagram in the category of unital rings. This one is in the category of unital rings. So we apply K0 And we get the following diagram here. This is phi plus star. Now k0 of R and k0 of S are defined to be the kernels. K0 prime of R and k0 prime of S are defined to be the kernels of these two arrows respectively. So we have the following diagram. And moreover, the horizontal lines give us two split exact sequences. So we have this diagram, and from the exactness of the lines, we obviously observe that phi plus star restricts uniquely to a map from here to here, which makes the diagram commute. And we denote it by phi star. And clearly it's a group homomorphism because it's just a restriction of phi plus star. And it is induced by by phi, sorry. So, and by looking at this diagram, we see that k0 prime becomes a functor. K0 prime is a functor from the category of rings to the category of abelian groups. Okay, so let's now prove that k0 prime and k0 agree on the category of unital rings. We have the following proposition. For every unital ring R, there is a natural isomorphism between k0 of R and k0 prime of R. So after we prove this proposition, we will no longer use k0 prime, we will just write k0 R. Before we prove the result, let's make a short remark, which gives us, actually it's a remark and a little exercise at the same time. And this remark gives us an explicit form, form of an isomorphism, of the following isomorphism that we've already discussed, in fact. Some time ago we discussed that k0 is product preserving in the following sense. So let's now make this isomorphism a little bit more explicit. If we have two unital rings, R and S, unital rings, so we form the product. At this point, it's perhaps more natural to denote it as a product, not as a direct sum, but as a product, because it is actually a product in the category theoretic sense. So we have two projections of this product onto R and S respectively. Let's denote them by P1 and P2. Then we apply K0. To this diagram, and we get the following diagram. This is P1 star, and this is P2 star. So this diagram is a product diagram in the category of unital rings. So I claim that this diagram is a product diagram in the category of abelian groups. That is, if I form the product of k0 of R and k0 of S in the category of abelian groups, and draw here two canonical projections onto the direct summons, then there is a unique group isomorphism such that the diagram commutes. Okay, now let's now come back to our proposition. Now R is unital. So let's look at the respective unitization extension. So since R is unital, it's easily seen that its unitization is actually isomorphic as a ring to R plus Z. We have already discussed this phenomenon many times in the setting of algebras. So there is an isomorphism here, that's denoted by psi. Psi is a ring homomorphism, isomorphism, sorry, and it is explicitly given by the following formula. It takes R plus K1 to, oh sorry, just the other way around. It takes a pair, Rk, in this direct sum, to R plus K multiplied by the difference of two identities. The new identity of the unitization minus the identity in R. And this is a ring isomorphism. So here we have two projections. The projection onto the second summand, P2, and onto R, P1. Let's now apply K0 to this picture. K0 of R, K0 prime of R is the kernel of epsilon star. So we have the following split exact sequence here. This is epsilon star. Well, here we have a K0 of R plus Z, K0 of Z, and the projection onto the P2 star induced by the projection P2, and the projection induced by P1 onto K0 of R, P1 star. And here we have a isomorphism psi star. It's more or less immediate from the construction that this diagram commutes just by the construction of psi. This diagram commutes in the category of unital rings. So this diagram is also commutative because it is obtained by applying a functor. So it is commutative. And we now recall that K0 of this direct sum can be identified with the direct sum of the respective K0 groups, K0 of R plus K0 of Z, in such a way that this projection becomes just the projection onto the second summand. And now if we look at this group, we see that it can be embedded into here, just by the embedding onto the first direct summand. So we get a map here, which is just the embedding of this group onto the first summand. And because of this isomorphism, we get another split exact sequence of the following form. So this is just the embedding onto the first summand. This is the projection onto the second summand. Clearly it is exact. And now by the exactness of both lines and by the commutativity of the diagram, we see that psi star restricts to an isomorphism between the kernels of these two maps. That is between K0 of R and K0 prime of R. And so it is an isomorphism. So it's easy to deduce from the construction, and this is a little exercise for you, that this diagram is natural. This isomorphism between K0 of R and K0 prime of R is natural in R. And this completes the proof. So K0 prime and K0 agree on the unital rings. And because of this, we will no longer use the notation K0 prime. We will just denote this group by K0 of R. If our ring R is not just a ring, but is a K algebra, then it would be natural to define K0 of R entirely in the setting of K algebras. A little problem here is that our unitization that we've just used at this lecture, R plus, is not a K algebra, even if R is a K algebra. But there is a simple way out of the situation. And at this point, I'd like to make a little announcement. If R is a K algebra, or K is a field, or in fact K be any commutative ring, it doesn't matter, then we can define the so-called K unitization. K unitization of R is the following K algebra, R plus K, which as a K module is just the direct sum of R and something spanned by a single element denoted like this. And the multiplication is defined in exactly the same way as in the case where K is the integers. So this is an algebra with obvious multiplication. Again, just like in the case where K is the integers, we can consider the augmentation epsilon, or better epsilon K, which acts from the K unitization of R to the base ring little k. By the same formula, it takes R plus lambda 1 to lambda. And the announcement is that we will see that K0 of R is naturally isomorphic to the kernel of this map, of the induced map epsilon star from K0 of the K unitization of R to K0 of K. So in other words, we can replace everywhere the integers by the base ring little k, and everything works. So we get an equivalent definition of K0 of R.
Is it true that this definition does not depend on K?
Yeah, exactly. It doesn't depend on K in the sense that we can take the base ring K, but we can forget about the base ring and replace it by the integers, forget about the algebra structure, and consider R as just as a ring, and we get the same K0 of R. That's the point. So it doesn't depend on the choice of K, which is quite convenient. At this point, this is just an announcement, but we will prove it fairly soon. This will follow from a useful property of K0, which is called split exactness. At this point, it's probably appropriate to draw a parallel with a topological K theory. So suppose that X is a locally compact Hausdorff topological space. So let's recall that we defined the topological group K0 of X only in the case where X is compact. So what happens if X is no longer compact? How can we define K0 of X in this case? In fact, there are several reasonable ways of extending K0 to non-compact spaces, and in general they are not equivalent. Let's consider probably the most common way of defining K0 of X in the locally compact setting, which looks as follows. So we consider the one-point compactification of X, which is a compact space. We consider the inclusion map of infinity of this new point into X plus, as denoted by I. Then we have the induced map of K groups from K0 of X plus to K0 of the point, I star. And we define K0 of X to be the kernel of this map. This is the so-called K-theory with compact supports. There are some other ways of extending K0 to a non-compact setting. Well, for details, you may look into the well-known book by Fuchs and Fomenko on homotopic topology. This one has maybe a slightly unpleasant property that it is a functor, not to make it into a functor, we must consider only those maps between locally compact spaces which extend to a continuous maps between their one-point compactifications. And such an extension is possible if we work with proper maps, such that the preimage of every compact set is compact. So in a way, I claim that this functor is compatible with our algebraic K0 in the following sense. For every locally compact Hausdorff topological space, there is a natural isomorphism between the topological K0 and the K0 of the algebra C0 of x of continuous and vanishing at infinity functions on x. The proof is quite straightforward. We just look at the respective diagram. Let's do it here. So we have a K0 of the one-point compactification together with I star, which takes it onto the group K0 of the point. And here we have the kernel of this map, K0 of x. Now, by the Serre-Swan theorem, this group is isomorphic to K0 of the algebra of continuous functions on one-point compactification. And we know that this algebra is nothing but the unitization of C0 of x. Well, strictly speaking, we deal with complex unitizations at this point. Anyway, we have discussed this probably at the first lecture. Well, here we have the unitization extension. So by definition, K0 of C0 of x is the kernel of the canonical map from here to K0, well, not exactly by definition, but almost by definition, modulo this remark. So we use this remark in this case where little k is the field of complex numbers. Okay, now K0 of C, of course, is the group of integers. And for the same reason, the topological K0 of a point is also the group of integers. Because vector bundles over a point are just finite dimensional vector spaces, and projective module, finitely generated projective modules over the complex numbers are just complex vector spaces. So the isomorphism, both isomorphisms are given by the dimension of a vector space. Well, again, the diagram is commutative, and by the commutativity of the diagram, we get a unique isomorphism between these two groups. And this is exactly what we're looking for. Okay. Our next goal is to obtain a convenient description of K0. So we now come back to the algebraic setting, to the setting of not necessarily unital rings. So we want to obtain a description of K0 of R, both in the unital and in the non-unital cases, in terms of idempotence. In much the same way as we did for the semigroup V of R at the previous lecture. First of all, let's introduce some notation. If R is a ring, a unital ring, and n is a non-negative integer, then we denote by 1n, well, it would be a positive integer. We denote by 1n the identity of the matrix ring Mn of R, which is assumed to be canonically embedded into M infinity of R. So in most cases, we will interpret 1n as a certain element in M infinity of R given by the following matrix. Here we have an n by n identity matrix, and the remaining infinite parts are 0. So this is our first notation. And second, if we have a ring homomorphism phi from R to S, a ring homomorphism, not necessarily unital, just any ring homomorphism, then of course we can consider the induced maps, the induced homomorphisms between the matrix algebras from Mn of R to Mn of S, and also from M infinity of R to M infinity of S. So the induced homomorphisms are obtained just by applying phi to every entry of every matrix. These homomorphisms will be also denoted by the same letter, little phi. This is quite convenient, and I hope this will not cause any problem. And our last convention is about similarity of elements in matrix algebras. You have two idempotents, say E and F, in M infinity of R. Here R is assumed to be unital. And then we say that they are similar in M infinity of R. Well, strictly speaking, this makes no sense because M infinity of R is not unital, and our original definition of similar elements makes sense only for unital rings. So we say that they're similar in M infinity of R if they are in the same GL infinity of R orbit, which means that there exists a matrix, an infinite matrix in GL infinity of R such that U inverse equals F. So the difference between this notion and the usual similarity is that GL infinity of R is not a subset in M infinity of R. But nevertheless, it acts by conjugation, and we say that two idempotents are similar if this condition holds. So equivalently, this means that E and F are similar in the finite matrix ring M of R for some integer n. So this is just a convenient terminology. Okay, now let's look at a description of K0 in the terms of idempotence. We start with the unital case, which is quite straightforward. Proposition 1. Suppose that AR is a unital ring. Then, first of all, K0 of R consists of all elements of the following form. E minus F. So we take two idempotents, E and F. We consider their classes in K0 of R. So K0 of R consists of all differences of such classes. E and F are idempotents in M infinity of R. Or we can also replace F by an element of the form of this form, which we denote by 1n. E minus 1n, where E is an idempotent. And n is a non-negative integer. Two equivalence classes, say E and F, in K0 of R are equal if and only if they are stably equivalent in the following sense. E plus 1n is algebraically equivalent or equivalently similar in to 2f plus 1 in M infinity of R. So, by the way, let me recall, let me do it here, that if we adopt this definition of similarity in M infinity of R, it is actually equivalent to algebraic equivalence. Two idempotents are algebraically equivalent if and only if they are similar in M infinity of R. This follows from our earlier result that in any ring, two algebraically equivalent idempotents are, any two similar idempotents are algebraically equivalent. And if two idempotents are algebraically equivalent, they then become similar in the bigger matrix ring. So as a result, if we work from the very beginning with infinite matrices, then these two equivalence relations are the same. So these are our first proposition. Actually, there is nothing to prove here. If we recall the respective description of K0 of R in terms of finitely generated projective modules, the only difference is that here we replace isomorphism classes of projective modules by equivalence classes of projections. This projection actually corresponds to the free finitely generated module Rn. So this is exactly an equivalent form of our earlier description of K0, but now in terms of idempotents. Let's now turn to the non-unital case, which is slightly more delicate. Proposition 2. Suppose that R is a ring. At this point, it is not necessarily unital. Then K0 of R consists of elements of the following form: E minus 1n, where E is an idempotent in the infinite matrix ring over R plus. N is a non-negative integer. But this is not the end of the story, because if I stop here, then we'll get not K0 of R, but K0 of R plus. And to get K0 of R, we require that E minus 1n has coefficients. So this is a matrix. It has coefficients not in R plus, but in R. And this is exactly K0 of R. Let's now prove this result. It will be clear from the proof that this description is not entirely immediate from the definition. So let's take an element x. Let's take an element x, first of all, in K0 of R plus. So we know that it has the form E minus 1n, where E is an idempotent over r plus n is a non-negative integer. So what does it mean that x belongs to k0r? Well, k0r is the kernel of epsilon star. So this means that epsilon star applied to E is the same as epsilon star applied to 1n. This is just our definition of k0 of r. So epsilon star at the level of idempotent, it just introduces to the component-wise applying of epsilon. So this is the equivalence class of epsilon of E. And of course, epsilon takes 1n to 1n to the respective matrix considered over this matrix considered in R plus goes to the same matrix considered over the integers. So it goes to 1n. So we see that x sits in k0 bar if and only if these two elements are the same in k0 of z. That is, the respective idempotents. So this one and this one are equivalent, are stably equivalent. So two elements of k0 are the same if and only if they are stably equivalent in this sense. Look here. But this is not exactly what we want. If we look now here, we want to show that they are exactly the same, but they are not the same. They are only stably equivalent. So now our goal is to make them equal by changing the idempotent E. So actually, this will be done in two steps. First of all, we replace the stable equivalence by the equivalence, or currently by similarity. And in the second step, we replace similarity by the exact equality. So first of all, let's make this equality into a similarity. So they are the same. And so this means that if we apply this description, this means that there exists M such that epsilon of E plus 1m is similar to 1n plus 1m. That is to the matrix 1n plus m. Okay, so what's this? Epsilon of E can be written as epsilon of f, where f is E plus 1. E plus 1n. Now let's observe that the same element x in k0r can be written as f minus 1k, where k is just n plus m. We simply add the equivalence class on 1n to both to E and to 1n. So the resulting difference will be the same, of course. So x has this form. And now the advantage of this description is that epsilon of f is not just stably equivalent, but is in fact similar to 1k. But this is still not exactly what we're looking for. We want this element to be equal, but they are just similar. Well, to make them equal, we again slightly change f. So they are similar, and by definition of similarity, we can find an invertible matrix, not just invertible, a matrix V in GL infinity of Z. So they are similar in, of course, in M infinity of Z. So we can find a matrix V in GL infinity of Z such that V multiplied by epsilon of F and by V inverse is 1k. And let's now observe that GL infinity of Z is naturally embedded into GL infinity of R plus. Just every integer goes to the same integer multiplied by the identity of R plus. So we have this embedding, and so V becomes a matrix. V can be considered as a matrix over R plus. So let's now take our element little f, and let's conjugate it by the same matrix V. Then, of course, G is similar to f. So X can be written as G minus 1k. We simply replace f by G. They are similar. And if we apply epsilon to G, well, clearly epsilon is multiplicative and it takes V to itself because V has integer coefficients. So we get V epsilon of f, the inverse, which is 1k. So epsilon of G is equal to 1k, and this means exactly that G minus 1k has coefficients in R. And this is exactly what we wanted to prove. So we changed our original idempotent E by an equivalent idempotent G such that this condition is satisfied. And this completes the proof. Okay, now we are ready to prove two important properties of K0, namely half exactness and split exactness. Half exactness and split exactness of K0. Both these properties are closely linked to lifting idempotent, to lifting invertibles in matrix rings. So let's start with some preliminary remarks on lifting invertibles. Suppose we have a surjective ring homomorphism, say phi from R to S. What is this surjective unital ring homomorphism? So we have the following natural question. Of course, we can restrict phi to invertibles, and of course it takes invertibles to invertibles. So the question is the restricted map, which acts from R cross to S cross, that is, between groups of invertibles, is it surjective? That is it true that every invertible in S can be lifted to an invertible in R? Well, simple examples show that the answer is no in general. Perhaps the simplest example looks as follows. We consider the projection of the integers onto Z modulo P, where P is a prime number greater than or equal to phi. Of course, it is surjective, but not every invertible element in here lifts to an invertible element in here for the simple reason that this is a field. So every non-zero element here is invertible. And so we have exactly p minus 1 invertibles here, but only two invertibles here, 1 and minus 1. And so clearly the restricted map cannot be surjective in this case. At most, two invertibles can be lifted to Z. That is 1 and p minus 1. Of course, these rings are very far from being C-star algebras. We are mostly interested in C-star algebras. But it's also quite easy to construct a similar example in the C-star algebra setting. Let's take the closed unit disk D. This is the closed unit disk on the complex plane. So its boundary is the circle. So we can consider the restriction map from the algebra of continuous functions on the disk to the algebra of continuous functions on the circle, the restriction map. And of course it is surjective by the Titsui-Urson extension theorem. But if we restrict it to the invertibles, well, this map is not surjective. This is a simple topological case for U. So if it were surjective, then the identity map of the circle could be lifted to a non-zero function on the disk. And simple topological argument shows that this is impossible. So we see that in general, not every invertible element in S can be lifted to an invertible element in R. Fortunately, we have the following useful algebraic lemma, which is very simple but is very useful. It is due to Whitehead. So let phi be a unital ring homomorphism from R to S, unital and surjective ring homomorphism. Then, for every invertible matrix R, for every invertible matrix, let's denote it by A, with coefficients in S. The following matrix, A plus A inverse, so explicitly this is the 2n by 2n matrix of the following form. It sits in GL 2n of S. This matrix lifts to an invertible matrix over R. To an element of GL to n1. That is, we can always find an invertible matrix U in GL to n of R such that phi of U equals A plus A inverse. This lemma has many important corollaries in algebraic K-theory. In particular, it implies that the commutant of the group J infinity of R is generated by so-called elementary matrices. Well, we are not very much interested in algebraic K-theory, but this lemma is important in our case as well. So the proof is based on the following simple observation that this matrix, the matrix we are interested in, can be decomposed in the following product. Sorry. Well, this is a little trick. Just check and convince yourself that this is true. Why is it useful? Why is it useful? Well, we can now lift A to a matrix, not necessarily invertible, but to a matrix in Mn of R. And the same for minus A inverse. So we can find two matrices B and C over R such that phi of b equals a and phi of c equals minus a inverse. And now we define the matrix U as follows. So here we'll replace A by B. This is a 2 by 2 matrix over R. We replace this element by C, A by B. And this matrix lifts in exactly the same form to R. So this matrix sits in M2 of R. And it's easy to observe that all four matrices which appear in this decomposition all of them are invertible. This is a trivial exercise. For example, the inverse of the first matrix is, to get the inverse, we simply replace B by minus B. And here C by minus C. So all four matrices are invertible, and it follows from these two formulas that phi of U equals A plus A inverse. And this completes the proof. Well, now we are ready to prove the half exactness of K0. So we have the following theorem. So for every ring extension of the following form, the respective sequence of abelian groups K0 of I, K0 of R, and K0 of S is exact. So this is the half exactness of K0. As a first step in the proof of this theorem, I suggest you the following exercise, the following preliminary exercise. Suppose we have two rings, R and S, and consider the zero map from R to S. Of course, this is a ring homomorphism. In general, it is not unital, but it is a ring homomorphism, and K0 is a functor on the category of all rings, so it induces map 0 star from K0 of R to K0 of S. What is this map? So the exercise is to prove that this is what we can expect here. And this is a zero map between these two abelian groups. By the way, well, it is quite natural, of course, but this is not entirely obvious. So, in fact, when you try to prove this, you'll see that this is a little unpleasant diagram chasing here, if you do it just by definition. Okay, so now let's prove this theorem. Proof of theorem. Let's denote these maps by I and P. So here we have I star and P star. So first of all, since this is a ring extension, the composition of P and I is 0. So the induced map is 0 by this exercise. But on the other hand, this is pi star I star. And so the image of I star is contained in the kernel of P star. And we want to prove the opposite conclusion here. So let's take an element in the kernel of P star. So let's write it at, it sits in K0 of R, so we can write, by using our explicit description of K0 of R, we can write it as the difference of two elements, E minus 1n, where E is an idempotent in M infinity of R, n is a non-negative integer, and the difference E minus 1n has coefficients in R. We apply P, more exactly P star, so, or even more exactly P plus star. So P plus acts between the unitizations. So P applied to this difference is 0, P star applied to this difference is 0, and this means that since P star induced by P plus star, we see that P plus star applied to E, so the respective class is equal to the class of 1n in K0 of S plus.
E is an idempotent in M infinity of R plus.
R plus, thank you, of course. It is in an R plus, but the difference is in R. Thank you. Okay, so these elements are the same. Now we apply the same trick as in the proof of the previous proposition, and by applying the same trick, we may assume, without changing notation, that the respective elements, the respective idempotents, P plus of E and 1n are similar in M infinity of S plus. We may assume this just by replace, if necessary, E by E plus 1m for suitable m, and 1n by 1n plus m. Just like in the proof of our previous proposition. So in general, they are stably equivalent, but we add suitable 1m for suitable m and make them equivalent or equivalently similar. Okay, so they are similar, so we can find an invertible matrix V in GL of K for suitable K over S plus, such that V multiplied by P plus of E and by V inverse is equal to 1n for sufficiently large little k. It would be nice to lift V to an invertible matrix over R. This was possible when we proved the previous proposition, but in the previous proposition, S plus was just the integers. And of course, we can always lift an integer matrix to R plus. In this case, we cannot lift V in the general case, but by Whitehead's lemma, we can lift V plus V inverse. And let's do it. By Whitehead's lemma, we can find an invertible matrix U in GL 2K of R plus, such that P plus applied to U equals V plus V inverse. So U is invertible. Let's now take E and let's conjugate it by U. Or more explicitly, we write not E but E plus 0. So we add the 0 K by K matrix and let F denote the following element: U times E plus 0 times U inverse. Well, of course, this is also not important in M infinity over R plus. And of course, it is similar to E. So if we now apply P, more exactly P plus to F, P plus of F, what we get? We get V plus V inverse times F plus 0 E, not F. P plus of E plus E plus 0 projects onto P plus of E plus 0. And P of U inverse, clearly this is V inverse plus V. So we have three matrices, three block matrices. We multiply them. Of course, it suffices to multiply the blocks separately. And what we get is so we multiply this, this, and this, and we get 1n. And then when we multiply this, this, and this, we get 0. Which is, of course, identified with 1n. Okay, so what do we see? We see that the element f minus 1n sits in the kernel of P plus. Why is it useful? And what can we say about the kernel of P plus? We can describe this kernel quite explicitly. Let's observe that if we forget about the multiplication, then of course this sequence is exact. Just by assumption. So let's now observe that if we add identities here and here, it is still exact. Clearly, we take the direct sum of two exact sequences of abelian groups. And if we now apply matrices to all these, to all this sequence, of course we get again an exact sequence. This is I, and this is P plus. So the sequence is exact for every M. So the kernel of P plus is actually identified with MM of I. So we see that F minus 1n. So in our setting, little m is just 2k. It sits in M 2k over I. Well, this is a good news, because if we now look at F, what can we say about F? F, first of all, F was in here, in M2k over R plus. But now we see that it has the form 1n plus some element in M2k of I. So this implies that F sits in M2k over I plus. And so we can form an element in K0 of I, as denoted by Y, F minus 1n. And this element sits in K0 of I because this difference has coefficients in I. So this follows from our description of K0 of I in terms of idempotence. And after we apply the map I star induced by the inclusion of I into R, we see that it takes Y to X. Just compare this expression and, well, and this one. So in K0 of R, E equals F because of this. and so y goes exactly to x. So as a result, we see that x is in the image of I star, and this completes the proof. So the kernel of p plus is equal to the image of I star. Sorry, the kernel of p star is equal to the image of I star. Oh, it's time to finish. Well, okay, so that's all for today. At the next lecture, I'll give you some elementary examples which show that, in general, if we add 0 here or here, then the resultant sequences are not exact in general. That is, we can say that the functor k0 is only half exact. So in general, it is neither left exact nor right exact. It's only half exact. And then we'll discuss an important special case in which this functor is exact. So we will see that it takes every split ring extension into a split exact sequence of abelian groups. This is, of course, a special case, but it's quite useful. And then we specialize to C-star algebras and discuss some special properties of K0 var in the setting where our base ring is a C-star algebra. Okay, thank you.